Okay, so yesterday I think we left off with talking about this and how it works. And I introduced that there are neurons that are excitatory or stimulatory and neurons that can be inhibitory. And so I used that with the example of the quadriceps and the hamstring muscle, that we have a sensory neuron that communicates with two different neurons, and one is an excitatory or stimulatory neuron that triggers and is going to communicate with the hamstring to cause the hamstring to contract, while at the same time the second communication here is via this other motor neuron to the hamstring. Did I say hamstring before? Yeah. The quadriceps. All right. The quadriceps was going to contract the hamstring muscle, with the second motor neuron is going to inhibit that so that only one contracts and the one is relaxed. All right, and so that's where we left off. So what we're going to do today is start looking at exactly what goes on for this signal to be transmitted down the axon. And so a couple of things about a neuron is that it's polarized. Under resting conditions, the inside of a nerve cell membrane is negatively charged with respect to the outside due to these unequal distributions of positive and negative ions. And when it's in this state of electrical imbalance, where the inside is more negative than the outside, it's said to be polarized. So that's a new term there. So we measure this polarization by what we call the membrane potential. Membrane potential is the voltage difference across the membrane. Voltage is created by differences in the distribution of positive and negative ions across the membrane. So, and so what I want to do to illustrate this was part of our homework. So I actually have your homework packet out that I checked off yesterday. I'm going to pause in the notes for a second and go through that. And I don't think in this class we had started to go over that packet, had we? No.
We did the first page.
Do we do the first page? Should we go over the neuron? All right. Some classes I did and some classes I forgot. Which, by the way, is there anybody in this class that was absent and needs to show me that? Okay. So, so when we look at the next page then, thank you. The next page talks about this resting potential and the fact that the membrane is polarized. So let me pull up this picture here and erase Stower's stuff here. So we have this picture right here. And what we're looking at here is the membrane of the neuron. And so you can see here that here's the outside of the cell, the inside of the cell, and they give you a key here. And you have potassium pumps. The darker ones are sodium potassium pump. The darker ones are potassium channels, and then this one lighter one is a sodium channel. And so when I asked you here, where's the greater concentration of sodium ions, it shows you that sodium is the little dots here, and so your sodium ion concentration is greater outside the cell, so there's a higher sodium concentration here than inside the cell. And then it asks you where's the greater concentration of potassium. Potassium ions have the greater concentration inside. So then it asks you, Paul Anderson in the video gave an analogy. He was talking about a salty banana. Somebody want to explain that? How he was using this to help students remember where your original higher concentration of each of these are? That's correct. All right, so just a silly little way for you to remember where these original concentrations are highest. So then I'd asked you that the sodium ions will naturally want to flow. Well, they naturally want to flow from high to low concentration, so high concentrations on the outside, so they're going to want to flow into the cell. And it says, notice it says, if a channel allows, so it has to have, just because it wants to flow or going from high to low, you have to have the appropriate channel present there for it to be able to do that. Because can ions go through the lipid bilayer? No, they cannot. So they have to have channels there that are open and allow them to go through. And then potassium ions would naturally want to flow out of, and so we should have out of there, if there's a channel that allows. So then number 5 asks you, embedded in the membrane are various proteins, list them. So here are the proteins, the sodium-potassium pump, the potassium channels, and the sodium channels. Then it asks you which of these proteins is associated with active transport, and you should have that is the sodium-potassium pump is associated with active transport. But then it asks you, how do you know? So how do you know that it's active? Because it's a pump, so we learned that the word pump refers to active transport. And looking at this, if you look at the picture here, there's an arrow going out, and notice here there's 3 sodiums, and then there's an arrow going in, and we have 2 potassiums. Those are the potassiums. And so what the sodium-potassium pump does is, see, the sodiums are going to where there's a high concentration, so it's going from low to high. So that's also how we know that it's active transport. Whenever something is going from opposite of the concentration gradient, going from low to high, it involves energy in the form of ATP. So then when we say here about this protein pumps blank ions out of the cell. So it's sodium ions, but let's be specific. I'm going to put here 3 sodium ions out of the cell for every 2 potassiums coming in. And notice here it says, in order to maintain a charge differential. What that means is this is one of the ways in which this resting membrane potential is maintained, meaning that the inside of the cell is more negative than the outside of the cell, which, by the way, is what all these little negatives here are. So the inside of the cell is more negative compared to the outside of the cell, which is what the positives are. And so, referring back to when we talked about the sodium-potassium pump in our diffusion osmosis chapter, when the sodium-potassium pump pumps 3 sodiums out, which each sodium is a positive charge, and only pumps 2 potassiums back in, see, the cell loses 3 positive charges, gains only 2 back. So it has a net loss of positive charges, which then means the inside of the cell becomes more negative or less positive than the outside of the cell. All right, and so that's what it means in order to maintain this charge differential. So then number 6 on the top of the next page asks, notice the charge on the inside of the cell is more negative than on the outside of the cell. This initial charge differentiation sets up a voltage across the membrane. We say the value of the cell's resting membrane potential is, and we should have negative 70 millivolts. And the negative in front of it, what that means, the negative means that the inside of the cell is more negative respect to the outside of the cell. All right, that's what the negative means. The inside of the cell is more negative in respect to the outside of the cell. The 70 is the value. It's the value difference. It's on fire today over there. All right, so that's the value and the voltage difference. So then it asks you, propose an explanation for why there's an uneven distribution of charge across the membrane resulting in this potential. So the first reason I already went over. The first reason that there's a difference has to do with the sodium-potassium pump. The sodium is pumping 3 positives out, only pumping 2 positives back in, so the inside of the cell is losing positive charges, which means that it is becoming more negative compared to the outside. What's another reason, according to this picture, that the inside of the cell would be more negative than the outside of the cell? That's right. There's more potassium channels, which means then potassium, remember, will flow from high to low or go out of the cell. And so since there's more potassium channels, more potassium can leave. And there's only one sodium, so sodium can come in from high to low, but it's not as much sodium is going to come in, so you have more positives leaving than you have positives coming back in. And that also contributes to this negative charge. And one other thing that we'll talk about in our notes, but I'll just address here that this illustration doesn't address, is that there are also negative ions that are inside the cell that don't have proteins to go through, so those are kind of stuck inside the cell, which also contributes to the negativity inside the cell. All right, so therefore we have this resting potential of -70. So then they have the little paragraph that says when a neuron is at rest, it's constantly pumping sodium ions out and potassium ions in to maintain this potential across the membrane of -70. The outside of the neuron has a slightly positive charge and the inside has a slightly negative charge, and so therefore the sodium potassium pump works continuously as ions leak back in or out according to their concentration gradient. So all of these, so the sodium potassium pump is instrumental in always maintaining that there's a high sodium concentration on the outside and a high potassium concentration on the inside. And even though we have these leak channels, we never reach equilibrium. And we're going to see that the state that there is a high concentration of sodium on the outside is needed for a neuron to work. So if we don't have that and the sodium and potassiums did come into equilibrium inside and outside the cell, our neurons wouldn't work, it would very quickly die. All right, so it's important to maintain that. So sodium potassium pump, very important in that. So then the next part 3 says a stimulus is applied. So what I want to do before we go over the answers to that is I'm going to do a little drawing on the board to show what happens when a stimulus is applied, and then we'll come back to this just to kind of give you the big idea as far as how a neuron works. So I'm just going to put a disclaimer. I'm going to attempt to draw this neuron here. You probably won't be able to tell it's a neuron unless I'm telling you that it's a neuron. All right, so I'm going to draw the cell body. The cell body, what comes off of it that receives the stimulus? Dendrites, right? So here's our cell body. I'm just going to draw here a dendrite coming off here with these little protrusions. All right, I'm just going to draw one of them. And so that's your dendrite. That's your dendrite. And then now I'm going to draw the axon. Looks like a radish. Somebody just said so what I heard from the peanut gallery out there. And last hour I drew, you can kind of see it here, I drew 2 dendrites and it kind of looked like a moose or the head of antlers. So I tried to just draw one this way. All right, so this is your dendrite coming off of there. This is the cell body, this is the axon, and at the end you have the synaptic terminals here. All right. All right. Alrighty. So, a stimulus needs to be present. So here's the dendrite. The dendrite receives the stimulus, and so the stimulus can be different depending upon the type of neuron. So the stimulus, if it's a sensory neuron, remember sensory neurons sense information from the environment and take it to the central nervous system. So a sensory neuron would have receptors in the membrane that sense changes in pressure or pain or heat or thermal detection. And then a lot of neurons, though, are communicated with by another neuron. So here's the end of this neuron. This is where this neuron would communicate with another neuron. So I'm going to go ahead and draw the end. I'm going to draw the end of another neuron here. So here. All right, so this is the neuron that's going to communicate with this neuron. how do the cells communicate? They release signals, and this is comes in the cell signaling stuff that we learned. So this is going to release special signals. These signals that are released, these chemical signals from one neuron to communicate with another, are called neurotransmitters. So they're just a special kind of chemical signal. And so what happens is that in order for these neurons, this neuron to communicate with this neuron, what needs to be true about what's in the membrane here? When we talked about cell signaling. A receptor. There has to be an appropriate receptor in that membrane that neurotransmitter can bind to. And so in the membrane, let's pick a different color here, there are receptors. So I'm going to draw here this receptor here, but note I'm going to put a little line here. What that represents is that this receptor is also a gated ion channel. So this gate can open and close. And so it happens to be a ligand-gated ion channel.
Is that for all or just this particular?
Just this one. We're going to talk about more ion channels over here, and those are different. So this is a ligand-gated ion channel. What does that mean? So in this case, the ligand is the neurotransmitter. So the neurotransmitter comes over here and binds to this ligand-gated ion channel. What that triggers to happen is this ion channel, the gates open. And so, now, and it doesn't open unless that neurotransmitter binds. And so now this gate opens. So we can write here that this opens when the neurotransmitter binds. What can go through that? It's a gated ion channel. So let's talk about then what we learned just a minute ago about just the general structure of the neuron. So the general structure of the neuron, the inside has that resting potential of negative 70 millivolts, and meaning that the inside is more negative than the outside. And what contributed to that, just to tie in what we just learned, is the sodium-potassium pump. And you had more potassium ions, so you have potassium ion channels than sodium ion channels. So that is the things that we just talked about. And so where's naturally the higher concentration of sodium, inside or outside the cell?
Outside.
Outside. So I'm going to write just to remind us here that your higher sodium concentration is on the outside of the cell, then your higher potassium concentration is in the inside of the cell. The concentration brackets. So we needed to establish that, to going back to this, when this neurotransmitter binds and opens the gate, of the gated ion channel. It's an ion channel. What ion diffuses through there is sodium. So sodium, remember, is in higher concentration outside the cell. So sodium in higher concentration outside the cell, when that gate opens, sodium comes in. This is diffusion because sodium is going from high to low concentration. When sodium comes into the cell, what's going to happen to this negative 70 millivolts? What's going to happen to the charge inside of the cell?
It's going to become less negative.
It's going to become less negative, right, compared to the outside. So it's going to become more positive or less negative. So I'm going to go ahead and put each sodium here has a positive charge. So I'm going to put here the positive. And so this is going to decrease. This negative 70 millivolts that we originally started with is going to decrease. Or increase, I'm sorry, becoming more positive, less negative. And so that's the stimulus, and that's what the stimulus does. So now, what does this cause to happen? If this causes a change to occur inside the cell, like most chemical signaling does. So therefore, the sodiums come in, and that first change is going to occur at the first node. So going back to my axon, I don't have the nodes identified here, because what am I missing on my drawing? the Schwann cells. Remember the Schwann cells that create the node? So I don't have those drawn in there. So looking at this, I'm going to draw Schwann cell here, all right? It'd go around the whole thing here, and another Schwann cell. So I'm going to say that this is a node, this is a node, and this is a node. At the node of rendezvous, the axon is exposed. Now, what's true about these different nodes is that there are two other types of gated channels there. There are sodium and potassium gated channels, but they're a little bit different. Let me just draw them in here. I'm going to draw sodium in green, and they're gated, so I'm going to draw the little gates here. So at each node, I'm only going to draw one sodium, but there are more than one, and it's around. You have to imagine that this is a cylinder, so it would be down here as well, and so on and so forth. And then I'm going to do the potassium in red. The gates are all shut. So at resting, these gates are all shut. Now, what makes these two types of gated channels different than the stimulus here is these guys are this and this. These are what we call voltage gated channels. And what makes them different is they open and close in response to a change in voltage or charge. All right, this one opened because of a neurotransmitter binding to it. So what happens here is we have our stimulus, the neurotransmitter binds, gate opens, sodium rushes in, inside the cell becomes more positive. What happens is that positive charge changes, interacts with, these are proteins, remember they have that three-dimensional shape, interacts with the positive charges, interact with the way that the R groups are bonded together, changing the shape of the channel, which opens the gates. So this gate is going to open, but it only opens because of the positive charges from the which were ultimately due to the stimulus. Now, if this is a sodium channel right here, and now it's open, where's sodium going to go? Into or out of the cell? Into the cell. So sodium is going to come into the cell here through this open gate. Sodium comes into the cell at that particular point. Is the cell going to become positive, more positive, or more negative?
More positive.
More positive, because sodium has a positive charge. So it's going to become more positive in relationship to the outside of the cell. This is called depolarization. It's depolarized, becomes more positive. And so, so that's what happens at this first node. Now this positive charge eventually is going to change the shape of the next sodium gates at the next node. So therefore, as the sodium comes in here, it's going to trigger these gates to open at the next node. And so these sodium gates open, which means sodium is going to go in, and the inside of the cell becomes positive. And that was the job of this node here. The positive charge here was to transmit the signal down here, which then will transmit it here and eventually to the end of the cell. So this node has done its job. So do we want to keep the sodium coming in forever?
No.
No. So therefore, to stop that, the gate shuts. All right. So while this one sodium is coming in over here, this sodium gate now is going to close. But that's not going to take care of all the sodium inside and all these positive charges. So what we want to do is bring it back to its normal resting state, which is at negative 70 millivolts. So therefore, we shut the sodium so that no more positive charges go in. But what happens is, you guys hear it?
Yeah.
The potassium gates open. So now if the potassium gates open, where will potassium move? Out from high to low. So potassium goes from high to low, and potassium will go out. So what we're really doing is losing positive charges, which makes the inside of the cell go back to negative. So now it's not going to be positive anymore, it's going to be negative, and eventually we'll go back to that negative 70 millivolts in the resting potential. Will these potassium gates eventually shut? Yes. So these guys eventually shut, and this goes back to normal. While that's happening, the sodium over here is coming in, and so what's that going to trigger to happen over here? What opens?
Sodium.
The sodium gate over here opens. So over here, sodium enters. Inside the cell becomes positive or depolarized. At the same time, what goes on over here?
The potassium.
Potassium opens, and then potassium leaves, and what shuts?
Sodium.
Sodium shuts. And sodium shuts. And the inside of the cell goes from positive back to negative and goes back to normal. And so therefore this continues at every single node down this long axon until it gets to the end, which we'll talk about what happens at the end in a little bit here. All right, so that's what happens from stimulus and how the stimulus triggers these changes to happen and how that signal moves down the axon. So let's relate this now. Let's go back to that part in your homework packet, and we'll look at that. So for number one, underneath the depolarizing the membrane there, it asks you what changes occur as the dendrite plasma membrane is disturbed. What changes, the neurotransmitter binds, sodium, the ligand-gated ion channel opens, and sodium diffuses into the cell. So that's what happens. And then the next question asks you to describe what will happen to the charge. The charge becomes, the inside of the cell becomes more positive. All right, so or less negative. And that's called depolarization. Then it asks you on this neuron here to show the changes in charge on the diagram below. So it has at resting, you have this neuron with the inside of the cell more negative in respect to the outside of the cell. And it asks you to show the changes, and this is the cell body here. So the stimulus is going to start here at the dendrites, and then the signal is going to move in this direction. So what happens is when the inside, it doesn't leave a lot of room to put at the dendrites like I did there. That's why I made the dendrite so big. But the sodium channel opens and the inside of the cell becomes positive. That inside of the cell becoming positive is going to trigger, I'm just going to draw some Schwann cells here. It's going to cause that sodium channel, I shouldn't have drawn it like that, that sodium channel to open. Sodium goes in and the inside of the cell becomes positive. That triggers sodium channel at the next node for the inside of the cell to become positive. And so that's how it moves down the axon from node to node. So in number 2, it says this depolarization in the membrane results in, and you should have action potential. And I'm going to talk about action potential here a little bit more in just a minute here. 3 says the depolarization in one area may stimulate other sodium channels downstream. Downstream means at the next node. So this sodium channel opening and the inside of the cell being depolarized triggers sodium to over here to open. So it allows the flow of sodium ions into the membrane and then further depolarizes it. So then this is only showing you depolarize. And so we have repolarization, which is number 4 on the next page. So repolarization behind the action potential. So this now has triggered the sodium gates to open over here. So repolarization, that's what happens like on here, in this picture here. When the sodium came in, it triggered these gates to open, which then what happened at this to repolarize it? Sodium gates close, potassium gates open, and potassium comes in, inside the cell becomes more negative again. All right, and so that's, they call it repolarization because you're going back to what you started out with originally. All right, we were in a polarized state with the inside being more negative, and now we're going back to that. All right, and so that's, and then there's hyperpolarization. Hyperpolarization is that when the sodium gates shut and the potassium gates open, eventually these potassium gates do shut, or else potassium will continue to go out. And they do shut, but they're kind of slow to shut, so more potassium leaves to where the inside the cell becomes more negative than it originally started with. It goes to about negative 80 millivolts. So they call that hyperpolarization. Eventually it goes back to normal with the help of the sodium-potassium pump and goes back to negative 70. But in that brief, it's really only lasts like a millisecond or two. That brief time period where the cell is at negative millivolts, or negative 80 millivolts, a little bit more negative, it can't receive a signal. So it can't transmit it doesn't respond to a stimulus. So in number 5, when it describes where this is and what limitations the neuron has at this time, it can't respond to a stimulus at that time. And this occurs at each node at the very end when more potassiums leave because of that slow gauge shutting. So I'll show you that here. You can see that in that graph on the next page. The quiz there, I just want to point that out real quick. The answers to that, you could submit it and get the answers, but I'll just read them off just in case you didn't do that. Is C, B, C, A, A. All right? Any questions on that? I have to say, I thought for number 2, I personally, when I was doing this, I thought D could also be an answer. All right, on there, the sodium gates open while potassium gates. So during depolarization, which of the following statements about voltage ion channels is true. So depolarization is when the sodium gates open and you have the influx, that's this right here. So this is being depolarized, so sodium goes in. And so B, they said B is the answer. So sodium gates open before the potassium gates. The potassium gates do open, but not during depolarization. That's the confusing part here. They open in repolarization. So therefore, D I could see as an answer where the sodium gates open and the potassium gates close because they do remain closed during depolarization. All right. So if you put D, I would say that that's okay. All right. So then the next one is with this graph, and so this graph illustrates what happens at each node. And so this graph is not showing you what happens during the whole neuron, it's just showing you what happens at one particular node over time. And so here's your time and here's your membrane voltage. And A right here, this is negative 70, so this is your resting potential. So that's the start and of negative 70. And so relating this picture to this node here. So let's look at this node here. So before I started all this, before there was a stimulus, the gates were shut, inside the cell was negative 70, this is the resting potential. So then you get a stimulus, in this case it's a neurotransmitter, sodiums go in, the inside of the cell here becomes positive, which triggers these sodium gates to open, sodium to rush in, and so therefore the inside of the cell becomes more positive. That's what's going on here. So B is skyrocketing here, the membrane potential. That's due to that part right there. So for B, when the inside of the cell becomes more positive, what's the name for that? That's depolarization. So B is depolarization. And what causes, I'm going to cross these out as we use them. So what causes that to happen? Opening of the sodium gates, which allows sodium in, right? So therefore B, we can also write, notice here, sodium in. So sodium's going in there. Now this is happening at, this is what happens at one node. So the sodium coming in is going to trigger the sodium gates at the next node to open, but we're talking about what just happens at this node. So as that triggers this one to happen, this one, what's going to happen? The sodium gates shut, potassium gates open, potassium is going to leave, and the inside of the cell is going to become more negative again, which is why we see the membrane potential going down. So when it becomes more negative, this says polarization. I'm going to call it repolarization. That's what our book does because we're doing it again. We're going back to where we started with. And the inside of the cell is becoming more negative because what? K plus is going out. Absolutely. And then D, notice here we have a little dip below the -70. That's that hyperpolarization I was talking about here. So that's due to that potassium gate slow to shut, and therefore some more potassium leaves and causes it to become more negative. But notice here it goes back eventually to the resting potential, and so this part right here is like A here, and it's back at rest. So that's your hyperpolarization. And so so we have two that we still need to put. So E here is the dotted line here. We haven't talked about this. This is called threshold. This is the charge difference that needs to occur in order to generate an action potential or for the rest of this to happen. And so what happens here, remember, this is your first node. The inside of the cell becomes positive due to a stimulus, in this case the neurotransmitter. If this inside the cell doesn't become positive enough, if it doesn't reach that threshold potential, then that's not going to trigger an action potential here. So the sodium gates aren't going to open, and you're not going to get the start of this. All right. So the threshold is what the charge difference that needs to occur in order to stimulate the action potential. So the significance of that threshold value is that it needs to be reached in order to generate an action potential. And once it's reached, once the inside, so you have a stimulus and the inside of the cell becomes positive enough to trigger this gate to open, an action potential is going to occur here, which is going to trigger it to occur here, and so on and so forth. And that neuron is we call firing or sending that communication down the axon. All right? All right, so I'm not going to go over the last page yet because we haven't talked about what happens at the end, Jen. I want to do that first. But what I'd like you to do is now go back to your notes. And this is what I want you to do with your notes.
Mrs. Walker, so is this last line like...
Oh, I forgot the last line. Yeah, the action of the sodium-potassium pump. Sorry, guys, I forgot to put that in here. Action of sodium-potassium pump to maintain potential. That is... At any of these, it could be A here, anywhere where it's at the membrane potential, the resting potential at -70. So the sodium-potassium pump maintains that. So that could be here. It could be it's doing it here as well. Okay? All right, thank you. So what I'd like you to do is go back to the notes where we left off. And what I'd like you to do is, based upon our conversation, see if you can fill in the blanks. All right? From that. Okay? All right, so try that out. And you should be able to go through hyperpolarization. So you can stop when it gets to refractory period. So try and see if you guys can work together if you'd like to see if you can figure that out. Okay.
The New York one? Where? Oh, yeah.
And I was holding on to that 2% chance.
Oh, of course. I have my notes. Like, what? Really? Well, like, Nick applied for differential. Yeah. It scared me. But then again, I was sure about like how great it is. Like, I don't really like to go there like deep down.
I have like hard classes. I am really good at like everything else. Or stories, essays. I could do 2 hours. Alright, let's go.
So, the Did you write all that? I actually can focus today. Like,
All I can think about is weather and traffic.
no. Okay. I can't say I know how stressful it is, but I can kind of imagine how like where you are. My brother worked and my mom. Like how stressing it is. I don't want to like make generalizations right now. Keep you thinking about it.
And I mean, it's really
Like you just was really anxious. Yeah, I feel like I took all these classes so that I could get into your university. Work harder with this in mind.
right now.
Nothing matters. But at the same time, it does. So like, I was Oh, you can. Oh, I thought you were saying does that? Is that how you were saying stimulus could also be stimulus?
What happened?
Any of that? Yeah, it did. Here's the thing, he didn't put this on just because like right now I remember doing the tutorial, I remember the animation. I was like, it's cool. I feel like I seem pretty late today. Like you just want to like go wood or something. Do some yoga. So it makes it the rest of this is sort of the introduction and then it brings the challenge. Unable to like right here. Why is it? Oh yeah, sodium ion. Of course. I saw that yellow stuff. That's what I was like. What's the really easy smells very familiar. Place the name on it.
To you? No.
It makes more sense to me. It's strong enough.
The next sodium state.
Strong enough. Oh. Is it more or all? Wait, and all of it. Next one says all of that with this trace. There's a sequential change down the taxon. The notes are on the
Okay. Let's see.
Resting frequency? Did you like check your ears? How do you know that you're right? Did you check your inches on the computer? Did you like check your Usually people don't get It's a struggle. No, I really appreciate that. No, she's just the cables are off. The lights off. It's repolarization. It's important. That big space for now.
No longer.
When your letter N looks like an 8, it says 4. Five? What? Oh, okay, 5 hours until they refresh. You don't want to? You just need to like prepare yourself to.
Alright, yeah, we'll go over the answers here. Yeah, it's already 11:40. I'll go over the answers right at the beginning of the hour tomorrow. How about that? Alright, does that sound good? So. And then the only thing we have left to do, you guys, is what happens at the end. Alright, so we'll finish it up tomorrow. Alright?